Good morning, Sam.
Good afternoon to you, Michael.
If you could be in two places at once, where would you be and what would you do?
I feel like I would probably be on vacation and also able to work at like the same time.
Yeah,
Something like that. What about you?
I think that's the only correct answer, Sam. I I would be on a beach somewhere or on a mountain somewhere and also at work. And the reason why I'm asking this is that we are doing an episode all about quantum computing and the ability to be in more than one place, or in this case, quantum state, more on that later, at once. And it's one of the fundamental aspects of these computers. Buckle up, it's going to be a slightly mad episode, so I do hope you're ready. I'm Michael Baird.
I'm Sam Jarrell, and welcome to Technology Now from HPE.
Quantum computing has been around for a while, coming and going from the news as breakthroughs are made. Now, originally conceived in the early 1980s, it's captured the minds of technologists and the general public alike.
Given that we don't have quantum computers at home, it feels like the technology hasn't exactly moved all that quickly like it has with regular computers, right?
Yeah, absolutely. Quantum computers are quite a bit more complicated to build than a regular computer. In fact, the 2025 Nobel Prize in Physics was actually awarded to three men for their work in the 1980s on superconducting quantum circuits, which laid the foundation for quantum computing today. But despite their complications, the number of quantum bits, the quantum computer equivalent of a regular bit, has been doubling every year since 2018, and the trend is expected to continue for the next few years. So, while we aren't necessarily seeing results from them which directly benefit us yet, usable quantum computers are likely just over the horizon. So, to find out more about quantum computing and to lay a bit of a groundwork for what I'm sure will be many more quantum computing episodes to come, I spoke with Dr. Michaela Eichinger, a product solutions physicist at Quantum Machines.
But before we chat to Michaela, you mentioned superconducting quantum circuits earlier. Superconductors tend to need to be cooled to absolutely freezing temperatures, so I thought it would be interesting to take a look at how exactly we can do that. How do we create the coldest places in the universe right here on Earth? It's time for Technology Then. So superconductors need to be cold, right? But how cold can cold actually get? Michael, you've heard of absolute zero, right?
Trying to remember it from my GCSE physics. I think it's minus 273 degrees centigrade. I don't know this in Fahrenheit, but cold.
Very cold, right? But do you know like what it actually means? Like in physical terms, what does it mean for something to be at absolute zero?
I think it's where particles stop moving. So whether that's atoms or whatever, but like the colder it gets, the less stuff moves. I think that's what it is.
So absolute zero is the coldest possible temperature. If you wanted to put a number on it, it would be negative 273.15 degrees Celsius, which is negative 459.67 Fahrenheit, or simply just 0 Kelvin. If you think of heat as just another form of energy, though, then at absolute zero, there's no heat energy left at all. It still has a quality known as 0 point energy, which is like a base level vibration in the atoms themselves. But in terms of energy which can be removed to lower the temperature, there's nothing left. So why do we care about this? Well, this is an episode about quantum computers, and one of the biggest issues these computers face is that the quantum bits are inherently unstable. Cooling them down until they are close to absolute zero helps keep these quantum bits stable. Unfortunately, quantum computers need to be colder than outer space, which clocks in at a toastier minus 270 degrees Celsius, which is minus 450 degrees Fahrenheit. So how do we cool our quantum computer? Well, we use a dilution refrigerator, a device proposed back in the 1950s, which mixes two isotopes of liquid helium called helium-3 and helium-4. The dilution refrigerator uses a quantum mechanical process called phase separation to cool things down. When the helium-3 is added to the helium-4, it absorbs the energy out of the helium-4, forcing that temperature to plummet. Because supercold helium will not freeze under normal conditions, we can cool it more and more in the dilution refrigerator until the temperature drops to just like 5 to 10 millikelvin, at which point our quantum computer is nice and cold and ready to go.
And I thought I was smart by having my TV just controlled with one remote. That is next level smart. Now, the super cooled components are just one part of a quantum computer. So to find out more, I spoke with Dr. Michaela Eichinger, a product solutions physicist at Quantum Machines. And the first thing I wanted to know was simply, how did she get to where she is today?
So my background is in, experimental physics. I did a PhD in so-called superconducting qubits. And then during my PhD, I already was very exposed through friends to the deep tech industry and community. And I got very interested to, join a startup and learn more about product development, business development, and these kind of things. And now I get to basically sit exactly at this intersection between, research and science and product and business development.
Because quantum computing has always felt quite theoretical, but are we saying it's now maybe moving from being theoretical to being something that is starting to have some practical applications?
So maybe let's take this statement a little bit apart, because yes, I think 30 years or 40 years ago, quantum computers or building devices based on the principles of quantum physics was very theoretical. And so the past 2 decades especially, many, many labs and companies around the world have been trying to build now a quantum computer. And then, of course, it's still this open question, when is it useful? So we're still at the very early stages of building large-scale quantum processors, but we're seeing already very novel applications, especially when it comes to exploring novel and new physics, for instance.
Okay, well, I think that leads us really nicely to try and do something nice and simple and explain quantum computing in under 15 minutes. This is written by my producer. Producer Harry is also a physicist. So let's start with quantum mechanics 101 and define a few terms if that's okay. So let's start with a quantum computer. What is a quantum computer?
So I would say it's a new species of compute. So it's a device that is built on the foundational principles of quantum mechanics. And because of that, it gives us very unique new capabilities of solving problems that we haven't solved before.
You mentioned the phrase a qubit. What is a qubit?
So the fundamental building blocks of such a quantum computer are so-called quantum bits or qubits. I really like the light switch analogy. So a classical bit can be on or off, 0 or 1. But a quantum bit is more like a dimmer switch, where you have, of course, also on and off, but there are many, many states in between. So the quantum bit can have all of these in-between states. And we refer to this also as the quantum bit being in superposition. But this is very theoretical still. So what is a quantum bit if we're talking about hardware? And there it gets actually very interesting, because we have many, many systems in nature that can be a quantum bit, but we also manage to artificially engineer and build quantum bits.
So I understand the principle of a traditional bit is either on or off. And so you can use that to make calculations, or you can do useful things with it. But I don't really understand how it would be useful to have something that could be on or off, or an infinite number of positions between on or off. How can you actually do anything useful with that?
If you think about a simple problem or how a classical computer works, right? You have all of these zeros and one, these classical bits switching back and forth, and it's all a more serial process of finding the solution to a problem. And of course, we have, GPUs where we can do many of these processes in parallel. But intrinsically, it's still, serial processes that try to find a solution to a problem. And a quantum computer is fundamentally different, because you can basically bring a quantum bit in this superposition of many, many states and have a multi-dimensional space and parallelism that comes from the quantum bit itself and this superposition characteristic. And then there is one other characteristic that matters a lot is that you can also entangle multiple qubits. So what is entanglement? It just means that you can have multiple qubits and their state can be correlated to each other. You cannot find this in classical bits, but also this correlation across, many distances give you a novel way of thinking also differently about a problem and utilizing this for a computation.
Okay. My head is slightly hurting, but that's okay. I knew this was going to happen. What problems are good to use a quantum computer for?
Yes. So I think if we think about nature and the principles that, everything is built up on. So nature is fundamentally quantum mechanical. So of course, it's just natural if you want to simulate nature, simulate molecules, model new materials, new drugs, that we do this with the quantum computer, because the quantum computer is fundamentally also built on the principles of quantum mechanics.
And can you give any practical examples of what a quantum computer would be much better, much faster, give you better results than a traditional computer?
We have novel materials, so-called superconductors, which allow you to have an electrical current that runs without resistance. And unfortunately, these properties only pop up below certain temperatures. So right now, we need to cool these metals to below their so-called critical temperature to exhibit these superconducting properties. So there is the hunt for superconductors at room temperature, but this is a very hard physics problem. And quantum computers can actually help to find materials and material combinations that might exhibit this property at room temperature. And then it really revolutionizes everything, that utilizes metals and that could benefit from superconductors.
The sort of problem you talk about sounds like the sort of problems that we say that AI is good at. So obviously AI uses traditional computing, but it's approaching problems in what sounds like a similar-ish way to a quantum computer. How do those two relate? Do they compete? They
actually don't compete.
Good.
So first of all, AI is still built on traditional compute, right? And what is very important and often misunderstood is that we actually need a lot of classical compute for the quantum computer. So these days, we actually already also co-locating our quantum computers in data centers and HPC centers, because we need classical compute and AI to actually operate our quantum computer. So it's an integrated architecture that we're building, and we're working towards what we call a quantum supercomputer, actually. So the big goal is actually a quantum supercomputer where you have AI and quantum working hand in hand, amplifying each other. And it can go in both ways. It's, AI for quantum and quantum for AI. You will find use cases for both sides.
So they work in tandem. They can work in tandem.
Yeah.
Okay. So how do you actually build a quantum computer? Because I think this is the thing that I think is maybe the most interesting part of this conversation, because we've had conversations about quantum and quantum computers on the show before, and again, it sort of feels quite theoretical, but actually, I'd love to practically understand what are the building blocks.
It's an excellent question, and the great thing actually there are multiple correct answers to these questions, because there are multiple ways how to build a quantum computer, and it goes back to having these multiple options of how to realize a quantum bit. So there, for instance, in nature, atoms and ions, they already can be utilized as a quantum bit. So these types of quantum computers that are built, to me, they look quite messy, because you walk into a room and you see a lot of optical components standing on, mirrors and lenses and lasers. So it's huge infrastructure to trap multiple atoms and then control them via laser beams. And then on the other hand, which is maybe natural for many of the semiconductor industry and also more natural to me, is that you really have a silicon chip. You make electrical circuits on it using semiconductor fabrication technologies, but then you need to cool this chip to very cold temperatures, so much colder than outer space. And so you need this infrastructure to cool it. So it looks like a big box that hangs often from the ceiling, but it actually allows you to put the chip at the very bottom and have it cool to below minus 273 degrees Celsius. And this is just one part of the story because we have the chip, but then we need to operate this chip, right? Just having quantum bits on a chip doesn't give you a computer. So we will have many signal lines and cables going down to this chip. And then at room temperature, we will have boxes that generate signals that go down to this chip and back up, and that actually then perform and apply an algorithm, for instance.
There are quantum computers that exist today that you can do something with. They're not just theoretical, they're actual things.
There are actual things, and you will find them in many countries and in many companies and in many labs. And typically you can visit them quite easily as well, or even access them online these days.
What are the challenges with scaling it? Can you just, put some more chips, get some more hanging baskets?
That would be the great thing. And we're doing that. But the problem is that intrinsically, a quantum bit is a very fragile system. And it's very sensitive to its environment. So on one hand, actually, we would not like to, on one hand, we would like to isolate the quantum bit as much as possible. But then there is this trade-off because we want to do control and computation with it. So we need to connect to it. But that, of course, also induces error. It can destroy the quantum state. So the problem is to actually scale to many, many qubits and keep the system alive. So this is one big issue. And the more you scale, the more engineering challenges that you have.
And how big are the quantum computers at the moment in terms of qubits?
So there is a variation. For instance, on superconducting qubits, we are in the range between 100 and 300. And then we have neutral atom computers where we trap neutral atoms. And there we are actually already in the thousands. But they have different kind of capabilities and connectivity. But so in general, we cannot say that one modality is winning over the other because they all have currently their advantages and disadvantages.
From a practical sense, I guess from an organizational perspective, why is quantum computing something that organizations should care about?
I think this goes back to it being a new species or a new flavor of compute. Any kind of company that actually uses high performance compute, I think will benefit in the future from working also with quantum computers because they're already trying to solve problems in a space where quantum computers will be naturally good at.
I've been told it's not likely you'll be doing word processing on a quantum computer because it's not great at that. It's like playing to its strengths.
Exactly. So you will also not, open your email using a quantum computer.
Just fire up my quantum computer in the morning, open up my emails. Yeah, okay.
Maybe the email is there, maybe it isn't.
Yeah. Would a quantum computer be integrated into an existing system?
I think that's exactly the right term. We also now in the quantum space talk about classical compute as an accelerator for quantum compute.
Okay.
And that's why we will see this co-integration more and more.
Interesting. Yeah. Would you run AI on a quantum computer? Is that an application that would be great for it?
So there is a field that is explored, which is called quantum machine learning. So that is actually running AI on a quantum computer. I think this is also still, it's a bit controversial as well, I would say, in the community. But there is heavy, investment in exploring this avenue.
Okay, so we ask all of our guests that we interview about quantum computing this. What do you see as the timeline for a quantum computer? Like, are we in a bit of a quantum's arm race, so to speak?
We are definitely in a quantum's arm race. Every country, or so many countries now, have a national quantum initiative. There's lots of government funding, and private funding has been on the rise for this field as well. And what I've been seeing as well is export regulations, even on smaller quantum computing systems, right? So there is big national and global interest in building a large-scale quantum supercomputer. And the timelines, I think everybody's trying to, get really something useful done by the end of this decade.
What makes you most excited about the possibilities of a quantum computer?
So because I'm an experimental physicist by training, I'm very excited about, pushing the field of physics forward and discovering really new materials, I think, and in high temperature superconductors. Yeah.
Michaela, it's been absolutely fascinating chatting to you. Thank you so much for coming on to Technology Now.
Thanks for the invite. I really enjoyed it as well. Thank you so much.
When anyone talks about quantum, it is one of those things that I feel like goes way, way over my head, even when they're trying to bring it down to my level. But I do appreciate that you guys, had sort of a discussion around like, how do you even build these things? And what it seems to me is like temperature seems to be the piece that seems to like come back to everything here. We need the quantum computers to be incredibly cold, but then quantum could help us discover room temperature superconductors. And I feel as though it's all kind of like cyclical to some degree.
I bet quantum labs have got really good ice cream, because you're right, like it's all about keeping stuff cool, isn't it? I did find the analogy of the dimmer switch to be quite helpful to wrap my head around what she meant, or what is meant by a qubit. So that is, a normal bit is just like a normal light switch, on or off, 1 or a 0, whereas a qubit is a dimmer switch. So, and that is what they call a superposition. So it could be 1, 0, or any number in between. It's quite fascinating, but it's also quite daunting, I think, as a topic to sort of wrap your head around. I think we're going to be doing some more episodes on quantum computers, I think. What I also found fascinating was that quantum computers aren't just theoretical, they're actual things that exist. And I saw some photos of quantum computers from some other companies. And I think I described it in the interview as a hanging basket. And I think that's what it looks like to me. It's like this big, almost like dustbin hanging from the ceiling with all these wires coming out of it. I'm guessing to keep it very, very cool and for all the connectivity. But she said, they exist today and they can be accessed online. So they're cloud quantum computers.
Yeah, that's crazy to me. And does that mean like what? I could go to like a site for them and then I'd probably not leverage it, but I guess maybe you can watch people leveraging them.
I think when we interviewed Antonio Neri back in December, I think he mentioned that, quantum computers being an accelerator for a classical computer.
Yeah, he did. And I think that whenever we talk about these individual pieces, it always kind of also comes back to eventually them all sort of working together. Like her mentioning that they need to be located in HPC data centers because it needs classical compute, but then also to accelerate it, but then it needs classical AI to operate. It feels like it's all kind of a glimpse into a future where these things are not separate, but they're all part of one giant, powerful system.
Exactly. Yeah, I agree with you on that. Now, Sam, earlier on, you mentioned us not having quantum computers at home yet. And actually, that was something I wanted to ask Michaela. Given the advances we've seen in quantum computing over the past few years, will we ever have quantum laptops at home?
So quantum laptop, probably not in the near future, just because we also don't have high performance, computers, supercomputers at home. It's very big and bulky. So I don't see in the near future this being, collapsed to a little laptop. And it's probably also not necessary. But then the quantum cloud, actually we do have a quantum cloud because many quantum processors can be accessed via the cloud these days to also push the research and push and accelerate the progress on these devices.
Okay, that brings us to the end of Technology Now for this week. Thank you so much to our guest, Dr. Michaela Eichinger. And of course, to our listeners, thank you so much for joining us.
Yes, and if you've enjoyed this episode, please do let us know. Rate and review us wherever you listen to episodes. And if you want to get in contact with us, do make sure you send us an email to technologynow@hp.com. Man, there are so many subject line options. Subject line, superposition, or dimmer switch. Both of those are fine. And of course, don't forget to subscribe so you can listen first every week. Technology Now is hosted by Sam Jarrell and myself, Michael Bird, and this episode was produced by Harry Lampert and Izzy Clark, with production support from Alicia Kempson-Taylor, Becky Bird, Alyssa Mitri, and Renee Edwards. Our theme music was composed by Greg Hooper.
Our social editorial team is Rebecca Wissinger, Judy Ann Goldman, and Jacqueline Green, and our social media designers are Alejandra Garcia and Ambar Maldonado.
Technology Now is a Fresh Air production for Hewlett-Packard Enterprise, and we'll see you at the same time, the same place next week. Cheers.
Bye, y'all.